Okay, welcome to my presentation. Well, first I would like to start with the current status of GPUs on the Brutus cluster. I'm not going into details about Brutus itself, because I assume that most of you already heard of it and are more or less familiar with it. One thing that I would like to stress out is that the GPUs are fully integrated into the cluster. So there is no separate cluster or separate part. Using GPUs, it's just another set of compute nodes sharing the same network, sharing the same queuing system, the same users, like the normal nodes. Also, the nodes are, like all other compute nodes, not reserved exclusively. This means that your single GPU job will most likely end up running on a node running other GPU jobs of other users, or even maybe non-GPU jobs, if we don't have enough GPU jobs to fill it up. And in the batch system, this is just another resource. So as you can see here, if you log into the cluster to submit the GPU job, you just have to define the R GPU resource, and then it will end up on some node, which, as I explained, most likely will also be running other jobs. So now I'd like to go back to the history about how the GPUs evolved in the Brutus cluster and the CUDA releases. We started to play with the GPUs in the middle of 2009. Around this time, CUDA 2.3 was the most recent version. And our first experience with GPUs was to simply attach 2 Tesla nodes to our login nodes. So we had a total of 4 GPU nodes that the users could use interactively while logged into the cluster. Then in late February, March, we installed our first GPU compute nodes and integrated them in the cluster. Hardware-wise, this was 4 compute nodes. Each of them had 6 GPUs, or still has. They're still in production, with 12 cores. When we started with them, we were still running CUDA 2.3, the most recent release. And then later on, we migrated to 3.0. And at the end of June, CUDA 3.1 was released, which is a more or less important release, as it adds a feature called CUDA visible devices, which basically everyone needs if he wants to share GPUs among multiple jobs. But back then, in February, this feature simply didn't exist, so we had to build our own solution. And then later on, at the beginning of this year, we started with our Fermi nodes. That's 18 nodes. Each of them has 2 GPUs and 24 cores. And we also have one ATI compute node with ATI GPUs. So while integrating the GPUs, we had 3 big goals. One of them is flexibility. We wanted to support multiple generations and also vendors of GPUs. We don't like to be locked into Nvidia or only be able to support this type of GPU. We wanted to give the users a choice. Also, another important goal, if not the most important, was to maximize the resource utilization. As I already explained, we really wanted to be able to share the GPUs among multiple jobs. And then last but not least, it should be reasonably easy to use. So how does our solution look to this? Flexibility was more or less easy with platform LSF. At the moment, we are running version 7.1. And for the GPUs, we just had to define some new resources. So we tell LSF that this compute node has, for example, 6 GPUs. And we also define the type and the vendor in LSF so that the user can choose a specific model of the GPUs where his code will run. Now with the second goal, maximizing resource utilization, this is doable with CUDA 3.1, which was released in late June 2010. But as I explained before, it wasn't possible when we started with the GPUs. So we had to build our own solution. And the big problem is that CUDA is completely closed source software. So you cannot do anything about it. But we have full control about some other parts of the software stack where the application is running. So in this more or less incorrect graphic, you have on top the user application, which we could touch in some cases, but we don't really want to mess with it. Then we have the CUDA library and the kernel module. And in between, we have the glibc and the dynamic Linux loader, LD Linux. So this is what we used for our solution. We simply intercepted calls between the user application and the CUDA library. And so a library called libFairyDust was born, because it works like magic. You don't see anything. It uses the LD preload mechanism to hook between the between the application and the dynamic loader of Linux. And basically, it simply hijacks or intercepts all device-related function calls and implements all 3 APIs provided by CUDA, which is OpenCL, the CUDA driver API, and the CUDA runtime API. So now here we have a small example using the CUDA driver API. On the first line, we get the number of devices. And if you're running on the libFairyDust, the library will, on the fly, fix up the result reported by CUDA. So for example, if you are running on a host with 6 GPUs, but you are only allowed to see 1 GPU, it will simply overwrite the result of CUDA and write 1 to the defcoin pointer. The same happens with all other device-related functions, and for all functions which do not involve any device handles or device IDs, like CU-mem getInfo, it doesn't care. It's directly passed to the CUDA library. So now we will have a look at the CU device get function. So what happens under the hood if an application calls this function? So on top we have the user application, which calls CU device get a pointer and then argument 0, which means that the application would like to get the first physical GPU. And in most code that you see in the wild, this is always hard-coded, because people are developing sometimes on the workstation, they only have 1 GPU and they don't care or know about using multiple GPUs. So usually this function would be handled by the CUDA library, but in our case, it gets intercepted by libFairyDust, which runs in the same address space as the application, and also doesn't really know anything about the physical allocations of GPUs right now. So what it does is it connects to a daemon running on the local compute node called FairyDaemon, and sends its own PID to this process. Then this daemon will then search the procfs for the LSF launcher PID, read the environment to see how many GPUs the application is allowed to use, and send back an array with the physical GPU numbers that the application is allowed to use. Now, in this example, the application requested 2 GPUs and will be allowed to use the physical GPU number 2 and number 5. So now with this information, the library can call the real CUDA function, CU device get, and simply it fixes up the argument here. So you see in this array, the index number 0 is 2, so it replaced the 0 with the number 2. Then this gets passed to libCUDA. If everything goes well, CUDA writes the result back to the device pointer, and to make everything transparent, it also simulates that it rewrites the 0 back to the application so that the application doesn't really see that it's not running on the physical GPU number 0. And after this has been done, the control gets passed back to the library. Now, as I already mentioned, with the upgrade of CUDA 3.1, this became obsolete because then Nvidia finally decided to implement their own solution to this problem. And because, well, you see, it's a little bit complicated and it takes a little bit of maintenance work to keep this running. So we decided to drop our own API wrappers and use the native method of hiding GPUs from the application. But then we had another problem. When you submit the job in LSF, LSF can set the environment, but this can only be done when you submit the job. But you need to be able to set the CUDA visible devices environment variable while your job starts up, because at submission time you have no idea how the situation on the GPU node will look when your job starts up. So since we were already using the LD library, LD preload mess, we just decided to intercept another syscall, and the easiest candidate for this happens to be the IO control syscall. The whole communication between the CUDA user space library and the kernel module happens via IO control syscalls. So the CUDA 3.1 or 4.0 version of libFairyDust now looks like this. It's much simpler. Here you have the strace output of a typical application. And in this situation, it just started up, did its first call to the Nvidia library. So it opens the Nvidia control device and calls IO control, file handle, some special ID reserved by Nvidia, and the device pointer. So basically now we do the same like we did with the CUDA library, just with the libc. We hijack this IO control syscall, pass it to libFairyDust, and if the request ID matches the special ID, and if it was the first call, it does the same thing as it used to do before. It contacts the daemon running on the local node to see which devices are free, and instead of emulating or hijacking any Nvidia calls, it simply overwrites the environment of the running process, which is a no-brainer as we are running in the same address space. And later on, if this has done, it simply passes the function back to libc and goes back to the application. And a few lines later on, and the CUDA library will read the environment and be happy. So I've mentioned that we also have AMD and ATI GPUs. With AMD, I don't know, maybe with the latest release there is a native function to do this, like NVIDIA offered with the CUDA visible devices. But at least with Stream 2.4, I didn't find anything to do this. So since we already had the code to intercept OpenCL calls, and OpenCL is the only thing that AMD provides, we just did some copy-paste and use our CUDA 3.1 approach to hijack CL get device IDs. As I already mentioned, to run on the AMD GPUs, you just have to request this type, so it's completely transparent to the user. And the nice thing, if you're using the AMD SDK, you can also run your code on normal CPUs. Now, we've just talked about how the situation looks on the compute nodes. How does this fit together with our queuing system? Well, on the left-hand side, we have platform LSF, version 7.1. And the only job of LSF is to allocate resources on the cluster level. It dispatches job to the correct GPU type. So if the user requested to run on a Tesla node, it will make sure that it runs on a Tesla node. But it doesn't really care about GPUs at all. The only information that LSF has about GPUs is the number of free slots. So for example, it knows GPU node X has 6 GPUs, and it will simply count to 0. But it doesn't do any physical allocation. So this is why we had to build the Fairy daemon, which I already explained before. In contrast to LSF, it doesn't know anything about clusters. It doesn't care about other GPU nodes. It's just running on the local node and allocating the physical jobs to a GPU job. As I already explained, the communication between, let me put it in another way. Basically, the daemon running on the local compute node is the glue between the queuing system and the application running under the control of the library. And the communication between the batch system and the daemon is done by reading the environment, which LSF sets while starting a job. And as I already explained, the communication to the application or the library is done via TCP/IP, which happens always to be on the same node. So now we have some examples on how to submit GPU jobs on Brutus. As I already explained, we have 2 GPUs attached to each login node, which means after logging into the cluster, you can just start your GPU job and play with it interactively. And if you want to submit the job, you just have to do the normal bsub. In this example, we request 2 cores and the resource GPU. Now, in our environment, LSF allocates 1 GPU per core, which means in this example, you would end up running with 2 cores and 2 GPUs. And by default, we are selecting Fermi nodes with CUDA 4.0. You can also do more advanced stuff like running MPI jobs with a bigger amount of GPUs. Then the submission gets a little bit more complicated. Now in this example, we request 24 cores and 0.25 GPUs per core. So in the end, your application will end up running with 24 cores and 6 Fermi GPUs. If you want to run on the old hardware, you simply have to select the non-default GPU type Tesla. Then we select equals Tesla, and the R usage GPU goes like it would go while submitting a Fermi job. And the same is true for ATI GPUs. If you want to run on the ATI GPUs, simply load the SDK and select GPU type Cypress. Cypress is actually the non-marketing name of the AMD GPU line. So now about some other operational issues that we had apart from integrating the stuff into the batch system. Nvidia has one nasty feature or habit. The user space library has to exactly match the kernel driver. This means that you cannot provide multiple CUDA versions on the same host. This is the reason why we are installing new CUDA releases on request. So we do not want to run the latest bleeding edge version. We just install a new version if users are requesting it and tell all the remaining people to recompile the code because it breaks all existing binaries if you upgrade it. But we had some cases where users were unable to upgrade to 4.0 due to lack of time and they hit some bug in the new SDK. In this case, we will be the nice guys and simply leave the kernel version of some. I think last time we kept it on 2 compute nodes at an older version, and then the user simply has to select an older CUDA version while submitting its job. Now, also AMD GPUs are not perfect. One thing which drives me really crazy is that you need an X server running on the compute node, because the user space library of AMD doesn't directly communicate via, doesn't directly do calls to the kernel driver like it's the case in Nvidia. It always connects to the X server, and then the X server dispatches your stuff to the GPU, which is pretty insane. And getting X to run without the monitor can be a challenge. Also, in my opinion, the kernel driver is extremely unstable. I've managed to create kernel panics with a single OpenCL job. We will see if it gets better in newer releases. But on the bright side, it only implements OpenCL and seems to have a much more stable application binary interface. So I don't expect that the users have to recompile their code if we are switching to a newer release of the AMD SDK. For simple OpenCL applications, it also seems to be possible to use the Nvidia compiler to compile your code and then run it on AMD GPUs. It's not that I would recommend this, but it seems to be possible. Now, on the hardware side, we didn't really have much problems. We had some memory errors on the Tesla nodes, where we simply had to ship them back and get a replacement part from the vendor. So far, we had no or not many errors on the Fermi nodes. But one thing that I would like to mention is that Nvidia really should stay out of the hardware business. The Tesla T10-1U boxes, we ended up with having like 4 different revisions of the rack mount kits, and each of them was broken or crazy in its own way. And also the cabling is an adventure of its own. You can get these cables in 2 lengths. One of them is too short and the other one is too long. As you can see here, is if you have to do any maintenance on the compute node, you have to uncable the whole stuff. Yeah, that's basically it. Was the end of the presentation. So, any questions?